Hello everyone and welcome to this second video on the signed particle formulation of quantum mechanics. So in this video we are going to talk about the time-dependent many-body system and in particular simulations of time-dependent many-body systems. And although this might sound like a daunting task and a very complicated numerical simulation to perform, there are ways to actually do this. And one of these ways is by using the signed particle formulation of quantum mechanics. And this will be the focus on this video. So let's start from the quantum many-body problem, and so let's define the problem that we have at hand. The quantum many-body problem is actually a problem that can be subdivided in two different problems. The first one is the time-independent problem, and the second one is the time-dependent problem. The time-independent problem is important and has relevant applications in chemistry, for example. In this particular case, the equation that one uses for this kind of problems or this kind of quantum system is represented by the time-independent Schrödinger equation, which is shown here. And as you can see now, the biggest difficulty consists in the fact that this psi function, the wave function, is now depending on a certain number of variables that can be quite overwhelming. In particular, what we see here is that this is going to be proportional to the number of bodies that are involved in the system. So the more particles, let's say electrons, we have in a system, and the more difficult this equation becomes to solve. And again, this is important. It is important to solve this kind of equation, because if we can solve that, then we can perform, for example, what is called computational chemistry. So one can simulate quantum systems which consist in molecules, atoms, and things like this, and can predict how these chemical systems would behave in time. So, or more than in time, how this quantum system would behave in a stationary regime. So if we are interested in chemistry, for example, stationary regimes are important, and this is the equation that one could use. Of course, the way it is done nowadays is not really by using exactly this equation, which would be very difficult to solve, even in a discretized formulation. But so actually, this is not the equation that is being solved, and many methods exist to solve this equation. But the focus of our problem is actually the time-dependent problem. So we are interested in quantum many-body systems that evolve in time, and we are interested in the transitionary or in the transition regime that these systems can evolve into. So we are really interested in what we see, for example, at the bottom here of this slide, where essentially we see a three-dimensional system that is evolving in time. So in this case, one has to use the time-dependent Schrödinger equation that looks like this one, and again, the difficulty consists in the fact that now the configuration space for this wave function becomes very quickly very big. And actually, this number of variables here is going to be directly proportional to the number of bodies that are involved in the system. So the more the bodies, the more this equation is going to become. The good thing is that we don't actually have to use the time-dependent many-body Schrödinger equation to solve this kind of or to simulate this kind of quantum systems. And there are two papers that can help us to solve these kind of simulations, but not by using the Schrödinger equation directly, and not by using the concept of wave functions, but essentially we can solve these problems, or we can simulate these quantum systems by simply using the concept of signed particles. So the results and the theory that I am going to show in this video are based in these two papers that I am showing in this slide, so that anyone that is interested can go and download these papers where all the details can be found. So to continue with the quantum many-body problem, one of the first difficulty that we encounter is the concept of indistinguishability. In practice, in quantum mechanics, particles are not distinguishable, and not even in principle. So it means that practically all particles, or let's say all electrons, or so all equivalent particles in a way, they all have the same physical properties. So there is no way to distinguish between one electron, say, and another electron. And for the very same reason that we cannot distinguish those let's say two different electrons, then their trajectories are meaningless, because we cannot really follow trajectories of particles which are indistinguishable. So the system at the very end, the quantum system, the quantum many-body system, has to be considered as a whole. We are going to see what this means in the context, of course, of sign particles. One more thing that we have to bear in mind is the symmetry properties of these systems. When we are in the presence of fermions, so in practice, particles which are indistinguishable and particles which are, for example, electrons, in this case, we know that an antisymmetric wave function has to be used for this kind of systems in standard quantum mechanics based on the Schrödinger formalism. So in other words, we have to make sure that the initial conditions of a system made of fermions respect this antisymmetric property. In the very same way, this applies for particles known as bosons, for example, photons. In the case of bosons, it is known that their wave function is symmetric. And moreover, no matter if they are fermions or bosons, we have also the theorem of conservation of symmetry that essentially tells us that the symmetry properties of a many-body wave function imposed on the initial conditions of the system do not change during the whole evolution in time. So this means that if you start from an ensemble of fermions that have an antisymmetric wave function, this wave function will be antisymmetric during the whole simulation of the system, and the same applies for bosons. If you start from a symmetric wave function, if your simulation is correct, at the end you have to end up with a symmetric wave function again. So these are facts that we have to keep into account when we are going to deal with simulations of these systems, but by using sign particles. So we can now go through the three postulates which define the sign particle formulation of quantum mechanics, and this time we are going to go through the many-body version of these postulates. So the first postulate now is telling us that physical systems can still be described by means of sign particles, but now these sign particles are defined in a 2 times n times d dimensional phase space, where essentially these particles will still have a position x that is now n times d dimensional, and will have a momentum which is now an n times d dimensional momentum, and they will have position and momentum simultaneously, so just like classical particles. Again, these particles, which are now many-dimensional particles, they will still carry a sign which can be positive or negative. Postulate 3 remains the same. If we have two particles with opposite sign and they are in, let's say, the same phase space coordinates, then they annihilate because they don't contribute together to the prediction of the behavior of the quantum system. Postulate 2 remains more or less the same, but the formulas now are generalized. So a sign particle that is evolving, let's say, in a potential described by the function that I am showing here with the pointer of the mouse, behave as a field-less classical point particle again, just like it would happen before, but during the time interval dt, they create a pair of signed particles with a probability gamma that is now defined over a multidimensional space. So as you can see here, gamma function remains the same, but rather than have a one-dimensional momentum integral, now we have a many-dimensional momentum integral to solve. But once again, if one goes through the definition of momentum integral, one ends up having that the gamma function can be written as a sum of these terms here, where this function here is essentially the Wigner kernel defined now for a many-body system. So postulate 1 talks about initial conditions. And in this particular case, it's interesting to see how we can impose the symmetries of the system. So let's suppose that we have, for example, an ensemble of electrons that are interacting with each other, and this is the many-body system that we want to solve. So in this particular case, we know that electrons are fermions. So they respect the symmetry, the antisymmetric, they have antisymmetric property essentially. So if you take the wave function at initial conditions of the system in the standard formulation of quantum mechanics based on the Schrödinger formulation, essentially if you take two of these particles and you exchange their variables, practically the wave function would be still the same, but with a minus sign in front of it. So practically, whenever you exchange a couple of variables, you will change the sign of the wave function. So in the very same way we would have done for a single body system, we can take these let's say initial conditions that are represented by a symmetric or anti-symmetric wave function, and we can compute the quasi-distribution function that corresponds to it. So in this particular case, this is what you would see. And for a system of fermions, essentially the initial conditions should be written as later determinants so that the right symmetry is fulfilled by the initial conditions. So it is not so different from what we were doing for single body systems. It's just that now the configuration space is a multidimensional one, so more computation is required. Beyond what we have said so far, there are approximations that we can introduce so that the quantum many-body system becomes simpler to simulate, especially if we are in a time-dependent regime. So we can introduce, for example, the Born-Oppenheimer approximation, which can be utilized even in the context of signed particles. So Born-Oppenheimer approximation is usually used whenever we are in the presence of wave function. This is not the only way we can use it. So we can also adapt this to the formulation based on signed particles, and it would work anyway. It would provide the kind of advantages that we have also in the case of the standard formulation. So in this particular case, so how do we introduce the Born-Oppenheimer approximation? This is very simple. We still take for granted that atomic motion of electrons and nuclei can be separated because of the massive or because of the mass of the nuclei, which is very, very big compared to the one of an electron. To make a long story short, you have to think that more or less one electron is 2,000 times smaller than one proton. So this approximation makes actually sense. So nuclear kinetic energy, because protons or because the nucleus can be very massive, this kinetic energy can be completely neglected. So at the very end, we end up having electrons-nucleus interactions that are described by Coulomb potentials. So just like it would happen in the formulation of Schrödinger when we introduce Born-Oppenheimer approximation, the same things can be done with the signed particle formulation, and more or less very similar advantages are observed. In the same way, if we are dealing with chemical systems, but time-dependent chemical systems, so say we are interested in seeing, for example, a reaction that happens in time, practically we can, in this context, we can introduce the concept of pseudopotentials, just like we could introduce this concept when dealing with chemical systems based on the use of the Schrödinger formulation. So in this particular case, what we do is that we separate electrons in core electrons and valence electrons. And the core electrons are going to build up a pseudopotential that we use. So the pseudopotential becomes a level of simplification that we introduce in the system, but it provides a very, very interesting computational advantages, because we are now drastically reducing the number of electrons that we want to simulate in a chemical system. So pseudopotentials can be included and can be utilized in the context of signed particles. So I am mentioning that so that anyone that is interested in a time-dependent simulation of a chemical system knows that they can use pseudopotentials as well. So we will now go through several benchmarks and applications to show how the signed particle formulation can work and how it can simulate actual time-dependent many-body quantum systems. So in this particular case here, we are going to, first of all, we are going to focus on the H2 molecule, so on the hydrogen molecule. And what we are going to investigate here by applying the signed particle formulation is what kind of bond we can observe being created when two atoms of hydrogen are getting close. So we will study this first situation here that I am showing with the mouse pointer, which essentially consists of two hydrogen atoms being far apart. And then we'll study a system that is made of two hydrogen atoms that are very, very close now. And what we can see by applying the signed particles is that we observe what we would expect to observe. In the case of two atoms that are very far apart, essentially if we do the simulation of the electron distribution, we are going to find that there is a very high probability to find one electron close to the first nucleus or to the first atom of hydrogen atom, and there will be another peak of probability here that is centered around the second atom. But as you can see here, the profile of these two electrons is pretty flat. There is no bond that is being created. But as soon as these two atoms are very, very close, then you can see this is a cut of the density or probability of finding electrons that has been computed by using signed particles. You can see that now here the middle between these two peaks is not flat anymore like it would happen in here, but there is the creation of a bond that we can see from this area here, where the probability of finding an electron is now very, very high between these two peaks. So this shows that essentially if we want to apply the signed particle formulation to the study of time-dependent chemical systems, this is possible and it can be done, and one has just to use the approach that has been described earlier. In the same way, we can now go beyond Born-Oppenheimer approximation, and for example, we can show that we can study a hydrogen atom as a true two-body system. So we consider now one atom of hydrogen, but we consider that its nucleus and its one electron that is orbiting around the nucleus represent a whole system. So there is only one equation that is going essentially to describe these two objects, both the electron and the proton. If we do this, if we apply this version of the sign particle formulation, so if we apply the sign particle formulation beyond Born-Oppenheimer approximation, we observe very interesting things. So in this validation test, what we do is that we have one electron, one proton now that is in the center that you can see here, for example, and we have the initial distribution of the electron that is centered around the proton or around the nucleus. And a cut is made here on this plot here, and you can see in red we have the distribution of the proton, and in blue we have the distribution of the electron. These are the initial conditions of the system. We now let the system evolve in time, and after a long enough time, which in this particular case consists of, which is equivalent to 6 attoseconds, which is very, very long for an hydrogen atom, what we see is that the proton profile hasn't changed that much. It's actually the same, and we would have expected something like this because protons are massive compared to electrons. They are around 2,000 times bigger, so essentially nothing is going to happen for them in an hydrogen atom, or just a few things happen, not much. But if we look at the profile of the electron in time, things are drastically different. We can clearly see that the packet corresponding to the electron has evolved in time. And what is very interesting is that actually it has created one peak here that is very clear, and one peak here and one peak here that are not very clear, but they can be isolated numerically. And if you do the difference in position between this peak and, let's say, this peak here, what you obtain is that it's a number that is very, very close to the Bohr radius. And we didn't have to impose the Bohr radius anywhere in the simulation. We got it as a natural simulation of a hydrogen atom in a time-dependent fashion based on the use of sign particles. So this is another way to validate the sign particle formulation, but this is also another way to show that it is possible, by using this approach, to simulate many-body time-dependent quantum systems. So we can now go beyond and go, for example, towards the simulation of indistinguishable particles. So, and in this particular case, we can show that if we have two fermions and we get them in a certain situation, the Pauli exclusion principles start to emerge. So how does it work? So first of all, we start from initial conditions, but in this case, the initial conditions have to represent the fact that these are two identical fermions. The way we do that is that we start from two wave functions that have nothing to do with each other, and we create the corresponding Slater determinant, which is going to be now the initial wave function in the Schrödinger formulation. We can now transform this function through the Wigner-Weil transform, and we have the corresponding now quasi-distribution function that tells us how to distribute the sign particles in the discretized phase space. So now if we do that and we let the system evolve in time, this is what we observe in the configuration space. So this is the position, and this is the probability in arbitrary units. So what you can see is that initially we have two peaks, and this is no big deal. These two peaks, they correspond to the initial conditions of two electrons that are centered around these two centers. Now the way we have defined the initial conditions are equivalent in to say that this electron is going from left to right, and the second electron here is going from right to left. So in a way we are squeezing these two electrons against each other, and we want to see what happens with time. But we know that fermions don't want to be in the same position at the same time. They don't like it. So what we observe with time is that these two peaks, they become sharper and sharper and sharper, and the middle here becomes how can I say it becomes depleted. You can see that the peaks becomes way sharper and nothing happens in the middle here. So it's more or less like saying that these two electrons, you can push them one against the other, but they will never reach each other. And that is the emergence of the Pauli exclusion principle that we are seeing here in the one-dimensional space. We can now see this very same phenomenon, but this time in the phase space. So this axis now is going to be the position, but this axis here represent the momentum. And we have these two electrons which have different momenta. One is positive, the other is negative. So we are pushing them one against the other. But this time these electrons, they are evolving in the phase space. What we can see is that after some time, we see here that there is the development of a ring. And this ring here is very well known by physicists. This is called a Fermi hole. This Fermi hole is a typical signature of the presence of the Pauli exclusion principle. So this is again another way not only to validate the sign-particle formulation for time-dependent many-body quantum systems, but it's also a way to show that this is a practical way to simulate this kind of systems. We are not completely alone in this business. There are methods we can use to actually simulate these very difficult and very computationally demanding systems. This concludes these lessons. I thank you very much for your attention.